Hello my students. Today we are in lecture number 46 and we have entered in the next chapter. Okay, it is lecture 46 and the chapter it is 4th. Chapter 4 of NCERT, and the name of the chapter is Moving Charge and Magnetism. That is the magnetism. In short, I'm writing so that we can't use much space. Moving charge and magnetism. It is first lecture, that's why I'm writing here the moving charge and magnetism. My dear students, okay, this is your chapter. This student, we will start this particular chapter with the introduction of magnetic field. Okay, magnetic field. Do you know, my dear students, the source of magnetic field? Actually, we will discuss in very detail, but directly I'm telling you, try to recall your standard 10th you have studied and you have started that chapter, that is the I think magnetic effect of current. Okay, in that chapter you started with Oersted experiment, one experiment which was done by the Oersted. What that experiment was, actually, with a simple activity you used to understand, if you will take a electric current wire, okay, current carrying wire, and a cardboard, if you will just put this current carrying wire into the cardboard, sprinkle iron fillings over the board, and this two end of the conductor, it is connected with a cell. As soon as you switch on the cell, you find a very fine concentric circle irons by that iron fillings, and then you explain, that is actually the Oersted explain, the current carrying conductor is containing magnetic field around the conductor. Okay, so this current carrying conductor is one of the source of magnetic field, and that magnetic field arranges the iron fillings in concentric form. The second in also that concentric actually explains the magnetic field will be in a circular form. Okay, that is all about the matter to discuss later on, but here we are writing the source of magnetic field, and we are having the three sources. Remember, source of magnetic field will represent magnetic field by this B. It is vector quantity, that's what I'm putting here an arrow. Okay, the source 1 we have studied in electrostat. When this magnetic field generates, try to remember, when charge is in rest, then it produces only electric field, that is called also the static electricity. But when charge moving with constant velocity or variable velocity, it produces electric field as well as magnetic field. Yes, so the first source we are writing here, the moving charge. Moving charge, you can see the name of the chapter is also moving charge. So the moving charge will be the first source of magnetic field. The second source, what is the second source? Right now I have discussed current carrying conductor. Yes, so it is current conductor, it is the second source. And the third one, it is the magnet itself. It might be the natural magnet, that is called the lodestone, or the artificial magnet like the horseshoe magnet, C-shaped magnet, S-shaped magnet, ring magnet, whatever. So magnetic material. Okay, my student, so these are the three basic source of magnetic field. Remember, the magnetic field we are talking. Now we will discuss what is the SI unit of magnetic field. We will represent this magnetic field by B. Again I'm telling you now, SI unit, and the SI unit of magnetic field is Tesla. Remember, we use by capital T, Tesla. Okay, the another unit of this magnetic field as the CGS we are having, it is the Gauss. You remember the name of scientist Carl Friedrich Gauss that we have studied in last chapter, the Gauss law. In this chapter we will again study, actually after this chapter in magnetism, okay, magnetic material, we will study about this Gauss law in magnetism. So Gauss, we will write by the capital G. Okay, this Tesla is very big unit, that's why we'll use this Tesla with the mathematical form micro, milli, okay, pico, femto, etc. Here the relation between this CGS and SI, that is the Gauss and Tesla, 1 Tesla, it is equals 10 to the power 4 Gauss. You must remember this one. Okay, 1 Tesla 10 to the power 4 Gauss. Now if it is a magnetic field, if magnetic field is a vector quantity, then it is very important to how to represent this vector quantity on board or on copy. So I am explaining you, there are two symbol you have studied already in standard 10, so I am recalling you just, okay, two symbol you use, try to remember, dot and cross. This dot explain the magnetic field perpendicular outward from the plane of paper or the board, and this cross, it represent perpendicular into the paper or plane of cardboard. Okay, try to remember, you will never forget this dot and cross if you will just try to understand what I'm telling you over here. Okay, kindly write down till here. Okay, now my dear student, since in this lockdown period, morning evening, you are getting a very famous serial. It is going on your TV, on the television in your house. It is Ramayana, Mahabharata, Sri Krishna. You might have seen this arrow. This is the weapon of god and goddess. Okay, arrow. Suppose you can see this arrow and you relate this arrow with the vector that you have studied. In fact, you have studied this vector in this arrow in vector. Actually, this is called cross and this is pointed is called dot. Okay, this is called cross and this is called dot. I have taught you in vector, and the length of this arrow is magnitude and this head represent the direction. I hope you remember. Suppose this arrow is coming towards you. Okay, if this arrow is coming towards you, this one, it is coming towards you, then what you will see, dot or cross? Of course you will see the dot. And if it is coming towards you, you are looking into the this particular paper or this particular board, towards this board, and arrow is coming towards you, then you will see this dot. It means the perpendicular outward direction, okay, perpendicular outward direction will be considered as dot. Actually, we use this conventionally. All right, there's nothing scientific over here. Now the second, if you are looking, any arrow is going into the paper, then which portion you will see, dot or cross? Actually, you are not able to see dot, but you will see the cross. That's why the direction we use, actually not that's why, but I am just correlating over here for your remembrance. All right, so you will see cross, and if it is cross, then it means it is going into the paper. So whenever you find cross, so remember it is going into the paper. If you are looking any dot, remember it is coming out from the paper. All right, so this is the story behind the dot and cross. Now we will start this chapter. Actually, in this chapter you have to study two segments. One, it is the force, both the segment, it is based on the force. In first you have to study the force on charged particle, and second you have to study force on current carrying conductor. The different type of conductor, circular conductor, okay, the square conductor, the straight conductor, we will place into the magnetic field, and then we will try to calculate the amount of magnetic force, what magnitude of magnetic force acting on that conductor if it is kept in a magnetic field. And the one I have discussed, that is the force on charged particle. But very, very careful, which type of charged particle? Actually, the the name of this chapter was, try to recall, it was the moving charge and magnetism. So you will be able to find the force on moving charge. Okay, so we will limit about yourself on the moving charge. All right, so magnetic force on moving charge, if you want to write, then you can write, my dear student, magnetic force on moving charge particle experimentally. Okay, experimentally it was found. Remember, there is no such formula. Actually, experimentally it was observed that if any charged particle projected inside magnetic field experiences a force. Remember, if any charged particle you left in rest in magnetic field, it will not experience any force. Okay, but experimentally it was found that if any charged particle projected with some velocity into the magnetic field at certain angle, that is, there must be some certain criteria, then that charged particle start experiencing some force. Maybe this charged particle positive or negative, but that will experience a force actually. Okay, so we are going to just correlate and study that force. Okay, so what was the observation? After number of observation, the formula, we come along with the formula, we came with the formula actually. Okay, after number of observation, and directly I'm writing here the observation. What was the observation? Okay, so the first observation, here I'm writing that observation will give you the formula, my dear students. What is the topic? The topic, let me write the topic: force on moving charge in magnetic field. Remember students, I am explaining here the force on moving charge, but we are taking here the positive charge, because I will discuss here the magnitude and direction, and for magnitude it might be the positive or negative, the force will be same, but the direction will change for positive and negative. All the laws, it has been discussed in your course here about the positive charge. Okay, like to find the direction of force, you have to use Fleming's left hand rule. I will discuss few more very simple rule, but remember, positive charge, about the positive charge you have to be focused. Positive charge. Okay, my dear student. Now, what was the observation? I am writing here. Observation. I think I should refill the ink. Okay, observation. So observation was, as the charge, amount of charge increase. Remember, this was the experiment, the very simple experiment, and you can do the experiment. Experiment can be done. Actually, you require some lab to perform this experiment, but this experiment was done, and the changes was very easy if it was available in lab. As the magnitude of charge increase, it was observed that the force increase. Okay, yes, if the charge increase, boom, then force also increase. The second observation, what the scientists found, as the strength of magnetic field increase, the force again increase. Yes, if the magnetic field strength increase, then force again increase. As the velocity increase, again it was found that the force increase. Very fantastic result was coming. But it was also mentioned, it was also observed that if we project the charge with some velocity, remember, Q is directly, F is directly proportional to Q, directly proportional to V, directly proportional to V. But what we observe, we got, if charged particle projected along the magnetic field, we observe force is zero. Oh, there's no effect on the force. Okay, this was very fantastic. Okay, my dear students, what actually I am telling here, as it was found that perpendicular to the magnetic field, if this is the magnetic field, look at here, if this is the direction of magnetic field and charged particle projected in this direction, V, perpendicular, force was observed as maximum. Oh yes, it was the maximum. But as soon as if it is magnetic field and we left this, we projected at certain angle, that is V, then what we found the force is being decreased. Force is being decreased. Could you find the component of this V? This component of V will be V sine theta. It means there is, sorry, V cos theta, na? V cos theta. It means there is no force due to this V cos theta. Yes, you can see along the magnetic field force was 0. It means this component not participating to give the force. So which force? Which component? Yes, it is V sine theta. It was observed that the maximum for this velocity, the maximum force for this velocity, remember, at this angle, the maximum force will be on V sine theta. Yes. Now, using all this observation, we can move to the conclusion. Actually, the scientists moved to the conclusion. And what was the conclusion? He also find that increasing this V sine theta by increasing V or by increasing the value of sine theta, force were increasing. Okay, force was increasing. Then how they conclude? They conclude, and this will be your very important topic, my dear student. What was the conclusion? And he concluded, you can write in statement, my dear student, the force on, I'm telling you, you have to write this particular statement. Force on moving charge particle, force on moving charge particle inside magnetic field, or you can write the force on a charge particle projected inside magnetic field directly proportional to amount of charge, strength of magnetic field, and sine of angle of velocity. Okay, sorry, sine of angle of velocity not, but the sine component of velocity, that is the V sine theta. A proportionality will be here, and in SI unit that proportionality become 1. So we can write here the F is equals to QVB sine theta. Since this force is vector quantity, it means this can be also represented in vector form. Okay. To understand the direction of force, Fleming did some observations, some experiment, and he find the force for different charges, positive and negative. All right, my dear student, and then he given a general idea, that is the law that was considered the Fleming's law for finding the force. Fleming's left hand rule, actually not the law but the rule, left hand rule to find the direction of force. But anyhow, this is the magnitude of force. Remember, this is the magnitude. What is that magnitude? F is equals to QVB sine theta. And what will the maximum value of F, my dear student? F max will be QVB. All right. It means if you will project this charge particle perpendicular to the magnetic field, that charge particle will experience maximum force. All right. If you are projecting, sorry, I'm sweating. If you will project that charge particle parallel to the magnetic field, what will happen? You will find zero force. Okay. Charge will not experience any force, my dear student. All right. Now, let me wrap this. Now the direction of force. We'll do some practice also to remember this direction or to understand this direction of force. It was obtained by, you can obtain by Fleming's left hand rule. Fleming's left hand rule. And what was that rule, my dear student? It was very simple. Fleming's left hand rule. Actually, Fleming used three fingers to represent the direction of force. What was that? It was index finger. Look at here carefully. Here, sorry. Actually, yes, this one. The index finger, this one. All right. Index finger, this one. This is the middle finger, and this is the thumb. Okay, my dear student. So this one is the index finger. Remember, Fleming had the two rule, the left hand and right hand, both the rules. In both the rule you study, this index finger will give you the direction of magnetic field. Try to remember. Okay, this will be the magnetic field. All right. Yes, this is the magnetic field, direction of magnetic field. Which one? Yes, index. And then this one, this middle finger will be the direction of velocity. This middle one will give you the direction of velocity. Then this one, all right. Thus, thumb will be the direction of force. Thumb will be the direction, will give the direction of force. Okay. Now, try to understand what will be the direction of force if any charged particle is projected in a particular direction. Now look at here, my dear students. If any magnetic field is in this direction, okay, in this direction, for this board, okay, for this writing board from bottom to top, if this is the direction of magnetic field, and you remember this is for the positive charge. This is the very important, my dear student. What will be the direction for negative charge, sir? So for negative charge, you have to just reverse this direction. After using the same rule, you have to reverse. If the force, the direction of force, that is the direction of thumb, is coming along the x-axis, then you have to flip for the negative, that is along the minus x-axis. Nothing else. Nothing. You have to change more. All right. Now try to find out here. Here, what was the example? If this is the magnetic field, you have left the charge, you have projected the charge in this direction. What will be the direction of force? So, if this is the velocity, the projection of charge, this is the magnetic field, then this will be the force. Now, my dear students, here only I am just going to give you another rule, that is the very simple, that is the vector rule. You can see if this is the velocity, I have written this particular formula in a particular order. Q is the scalar quantity. Okay, don't look at it. Now V B sine theta. All right. So V, this one. Then after V, if you'll move to the B, this one. Okay, V and then V and then towards the B. Then this thumb will give the direction of force. Okay, V cross B. You have to write in this order only. V then B. Okay. QVB, try to remember. So if you kept your forefinger along this V and move towards the B, then the thumb will give you the direction of force. And then you can, if you forget this particular left rule, then you can find out with this right rule also, thumb rule, which was given by the Maxwell. All right, there are a number of rule has been explained in your books, the different books. Okay, screw rule, swimmer's rule, palm rule, and XYZ rule. But you have to be focused about the concept if you are using this one, because this is very important for the vector also. If you have written the vector A cross B, then you used to put your forefinger along A and go towards B. Then this is the product, that is the A cross B. Likewise here, you can write this one in vector form. Kindly note down. You can write this is in vector form. F is equals to Q V cross B. This V cross B can written as a V B sine theta. Yes. So this is in vector form. So folding your forefinger from B, you will go towards B. Then you will get the direction of force by this thumb. Here I am giving you some examples. Suppose this is the direction of magnetic field, my dear student. a charge enters, positive charge I'm talking about, a charge enters like this way. Okay, this is the direction of velocity plus q. What will be the direction of force? What will be the direction of force? Okay, try to find out. The magnetic field, the direction of magnetic field, can you find out? Yes, it is downward. So put your forefinger towards velocity. Yes, and magnetic field is downward. You can put your forefinger in this way also, no? In this way also, but you have to fold this forefinger so that it goes towards the magnetic field. So you have to keep in this way. As you will fold your forefinger, you will move downward towards the magnetic field. From velocity, it is moving down, that is towards the magnetic field, and then this is the direction of force. It means the charge will experience a force in upward direction, and if charge is going in this direction and a force acting in this direction, then what will happen? It will start moving in this way. All right. Why I have made this as the circle, I will explain you later on, but the next example. Okay, in the same field, that is the cross field, if I project a charge from here, could you find the direction? If it is the point charge, positive charge, what will be the direction of force? How this charge particle will rotate? But one thing which is very important, try to remember, it will rotate, it will move on circular path. Whether it will complete the circular path or not, it will leave the magnetic field, it will be the matter of discussion, but it will move on circular path. I will discuss later on. But what will the direction? Okay, let me do again the rule. This is the direction of velocity. Then I have to put my forefinger in this direction, but I have to move downward. I cannot move my forefinger in this way because I'm very common man. I am the natural man. Okay, so the very common man and the simple man cannot move the hand in this way. So let me put my forefinger like this one. Okay, this one, and then I will move down, so the forefinger in this direction. Okay, so it will, the force will act in this direction and it will round this way. That is anti-clockwise, and this is also anti-clockwise. All right, now you can find out the direction for anyone. I am giving you few more example. We will discuss in very detail about this force. We will study about the motion. Okay, motion. If you will project, what will happen, the condition, how the charge will leave the particular space of magnetic field. All right, now the few more example I'm giving you. Suppose this is the magnetic field. Dot. Okay, if you projected an electron from here, electron is projected. Now the question, in which direction it will move, whether it will move or not? The answer is yes, it will move. This is the example. Answer yes, it will move, but now the question, in which direction it will start rotating? So we are going to find out here the direction for positive charge, and then we will flip the direction of force. You can see the magnetic field is in upward direction. Okay, it is dot, it is in upward direction, like this way. Okay, like this way, and this is the direction of motion. It means you have to put your forefinger in this way. The force will be in this direction, but for positive charge. If it is negative charge, then you have to flip your thumb. So this electron will move in this direction. What is this direction, clockwise or anti-clockwise? Anti-clockwise. Okay, again the dot field, uniform magnetic field. If you project an alpha particle, okay, an alpha particle, it is the alpha particle, what will be the orientation of its movement? Kindly find out. If it is alpha particle, the magnetic field is in upward direction, the velocity in this direction, what will happen? The force will be perpendicular. Remember, the force will be perpendicular. Here, as this charge enter, the force act perpendicular. As it will move, the force will be perpendicular. Always try to represent the force perpendicular. Now, as it will go, the force will be in this direction. Okay, force will be in this direction. But yes, and this is the positive charge, of course, so it will start rotating in this way, my dear student. Clockwise or anti-clockwise? The answer is clockwise. Now I am going to discuss why this is circulate, why this circulates. Okay, why charged particle circulates into the magnetic field. In this way you can find out the direction, my dear students. I'm not giving you any homework for today, but next day we will do the number of questions, now practices over here, and it is very important to find the direction, because the number of question you will find and you confuse with the direction, and then your entire level will goes in vain. Okay, here this is the direction of field. Be careful, my dear students, while listening. As you project a charged particle, positive charged particle with some velocity, and it enter into the magnetic field. Suppose here the magnetic field started. Actually, magnetic field started over here. Let's suppose magnetic field over here. In which direction force act? Force actually act perpendicular. All right. As the charge is going, due to perpendicular force, what will happen? Due to some component of velocity, the charge will deflect. Now it moves some distance. Again the force will be perpendicular. All right. Again it will deflect, and so on. So you can see this charged particle is turning, and it turns continuously because the continuously a force acting. That's why this charged particle start moving on a circular track. So kindly note down, the point I'm telling you, whenever any charged particle projected inside magnetic field, it moves on circular path. Now my dear students, if it is moving on circular path, one force it is acting, magnetic force, then due to motion of charged particle on circular path, there will be change in speed and the change in velocity, not the speed, change in velocity, and due to change in velocity there must be some acceleration. It means the particle will experience a force, and that will be the centripetal force. All right, that centripetal force will be balanced by which force? Magnetic force. And using this concept we will correlate. Okay, we will find some quantities like radius of circular track. What will be the radius of circular track on which this particle move? What will be the frequency with which it circulates? What will be the time period it took to complete one motion, one oscillation? And what will be the angular velocity, kinetic energy, whether the velocity changes, that is move in circular path, whether the magnetic field has capability to change the speed of circulating path. If it is moving with the 10 meter per second, enter with the 10 meter per second, can the velocity goes down or up while moving or after moving inside the magnetic field? These will be the number of questions in our mind, my dear students, and that all question will solve, that all the answers will get in my next lecture. Okay, my dear students, so we are concluding with this word today's lecture. Thank you, students.